Hello students, welcome to the first tutorial on linear motion. In this tutorial, we're going to focus on velocity time graphs and how to handle questions based on velocity time graphs. So in this video, we assume that you've seen velocity time graphs before, you have gone through them before, you've learned them before. So we don't really go in details about what velocity time graphs are. All we want to see is what are some of the most common questions that you can encounter on velocity time graphs and how can you handle them? So basically just looking at the math that takes place when you're working with velocity time graphs. But to start with, let's just put it out there to say what a velocity time graph is. So a velocity time graph is basically just a graph that is going to give you the relationship between velocity and time. So it's just a graph that shows the variations of velocity with time. So we have velocity in meters per second and time on the horizontal in seconds. So this graph is showing that it's going to be tracking how velocity changes of a particular object with time. So what do we need when it comes to velocity time? What are some of the key pointers that we need to work out problems? Well, basically there's just one main point here, and that is when it comes to a velocity time graph, to calculate the distance or the displacement. So to get the displacement of a velocity time graph, so the displacement will always be equal to the area under the graph. So the displacement or the distance covered, let me just say distance here, the displacement. So the distance covered by a velocity time graph, so the distance will actually be, in magnitude, it will be equal to the area under the graph. So in other words, if you can get the area under the graph for a velocity time graph, then by value, that value that you will find for the area, it is actually equivalent to the distance covered by that particular object. So with this in mind, this description, the distance covered is equal to the area under the graph. How can we use this to work out various problems? Okay, so let's quickly look at some questions. Let's start with one simple one. Let's quickly go through it and see how we can work it out. So here we're saying the velocity time graph of a runner is shown in the figure. How far does the runner go in 16 seconds? What is the acceleration of the runner at t is equals to 2 seconds and at t is equals to 11 seconds? So for this question, they're saying they're tracking, or we're tracking, the velocity of the runner with time. And here, if you can follow through, you're seeing that the time is being monitored in steps of 2 seconds. So you have 2, then you have a 4 there, 6, 8, just like that, up to 16. So the first question, what they want us to find is how far does the runner go in the 16 seconds? So 16 seconds is all the way up to that far end. How far does the runner go? So we're trying to get the distance that the runner covers in 16 seconds. Now, to calculate the distance, of course, we remember that point. The distance covered is equal to the area under the graph. But how can we get the area here? So what you have to do here is you have to separate this into shapes that you're familiar with. Most students will be familiar with the area of a right-angled triangle and the area of a rectangle or a square. So in such a case, the student might want to break this up so that you only have triangles whose area you can calculate, or LB. So these are the formulas for the area of the specific shapes here. But if you can remember, you can also deal with a trapezium. So if you can have a trapezium, then you can also work it out for a trapezium, because the area of a trapezium is just half A plus B H, where A and B are the two parallel sides, and H is the distance between the two parallel sides. Okay, so with this in mind, let's try to create our shapes here and see how we can calculate the area of those shapes. So it's up to you with which approach you want to take. But what you should see here is that you can practically split it here. You can cut it at this point, let's say. Okay, so you can say you have this. So this is a triangle. You can say this is going to give you area 1. After that, you can say you have this shape here. You can say this is a rectangle, that is area 2. After that, you can cut it here. And you can say you have a trapezium here. So if you're not comfortable with the trapezium, you can split the trapezium so that you get a triangle on top and the rectangle down. But of course, I'm going to deal with a trapezium, area 3. And lastly, we have a rectangle down here, and this is going to be area 4. So with that in mind, let's see how we can get the total area, the area under the graph. So for the area under the graph, first we get A1. A1 is a triangle, this triangle here. So if I work it out, it's half. The base is from 0 to 2, so that's 2. The height is from 0 all the way up to 8, so the height is 8. So if I multiply this, I get A1 is equal to 8. Then I move on to A2. A2 is a rectangle here. BS, base times height, or base times length. So the base is basically from 2 all the way up to 10. So I'm saying this is 4, meaning this has to be 6, this is 8, this has to be 10. So it is from 2 to 10, so the base is 8 here. Notice that if I picked 10 here, it would have been measured from 0, but I don't want that. I want to measure it from where it's starting from to where the shape is ending. So it is from 2 to 10. So you see that the gap between them, or this side, is basically just 8. So what I have is 8 multiplying the other side from this point all the way up. Again, this is an 8. So again, we have 8. So we have 8 by 8, and this gives us 64. Next, we move on to A3. A3, I decided to work with the trapezium. So the formula for a trapezium, area of a trapezium, we have it there. So the two parallel sides, now you notice that it's this one, this side, and the short one, the other side. So it's up to me which one I want to take as my A and my B. So I'm going to take this side as my A, and I'm seeing that this side is from 0 to 8. So what I have here is 1 over 2, and I have 8 this side plus the short one, the short side. This point here, this marks my 4. So this is 4, then 8. This 4 is supposed to be right on top there. So this is 4 here. The short side here, in other words, on the other side, it's a 4. So I have 8 plus 4. And then the height. For trapezium, we have height there multiplying at the far end. And what's the height? The height is the separation of distance between the two parallel sides. And I'm saying it is from 10 to 12. So the gap between the two parallel sides is a 2. So I have 2 this side. So if I worked it out, half of 2 is 1. Then I have 8 plus 4 and get 12. So this is just equal to 12. Lastly, we get A4. Now we move on to get A4. A4 is that last shape there, which is that our rectangle. So we're seeing that the base here is 4. It's from 12 to 16. So that's 4. And then the height is from 0 to 4. So we have 4 from the base, 4 from the height. So we have 16. So it's 4 by 4. And this is giving us 16. Okay, now we've got the small shapes that we created. To get the total area, I can write 80. We have to add all those individual shapes, A1, A2, A3, plus A4. And if we added them, A1 was 8, so we have 8 plus 64 plus 12 plus 16. So we see that the total area for our shape, if we try to add 8 plus 12, that's 20. 20 plus 64, that's 84. 84 plus 16, we get 100. So the total area is just 100. Now remember, the distance covered is equal to the area under the graph. And the area under the graph for the 16 seconds is that 100. So implying that the distance covered in the 16 seconds is actually 100. But since this is distance, this is meters. So that becomes the distance covered during that 16 seconds. Okay, that was the first part. What else are they saying? Well, in the second part, let me just erase everything here. In the second part, they're saying one thing. They're saying, what is the acceleration of the runner at t is equals to 2 seconds? T is equals to 2 seconds occurs here. So again, we're saying, for what you have to remember here is that the acceleration of an object is basically equal to the gradient of the graph at that particular point. And we're saying, and in this case, the gradient is constant since we have a straight slanting line. So the gradient throughout this line is going to be constant, implying that the acceleration is constant throughout up to the 2 seconds. So all we have to do is to get the acceleration during the first 2 seconds, and that will be the acceleration even at 2 seconds. So how do we work it out? Well, to get acceleration, we need the initial velocity, the final velocity, and the time it takes to change from that initial to the final. So if we look at this, what we have is, we have an initial velocity. This runner started from rest. The final velocity, if you look at the graph, that's 8 meters per second, and it takes 2 seconds to make the change. So the formula for acceleration from the definition, acceleration is defined as the rate of change of velocity with time. So we have the change of velocity over time. From here, the final velocity is that 8 meters per second. The initial velocity is 0, and it changes in 2 seconds. So from here, if you do the math, you get the acceleration as 4 meters per second squared. So that comes out as our acceleration at 2 seconds. Okay. Next up, they want us to get the acceleration at t is equals to 11 seconds. So where is t equal to 11 seconds? Well, we know here it's 10, and the next one is going to be 12. So 11 seconds has to be here. So we want to find the acceleration at that particular point. So again, we're saying for a straight line like this one, the gradient is the same throughout this line, implying that the acceleration will also be the same throughout this line, since the gradient gives us the acceleration. By velocity time graph, gradient gives us the acceleration. So in other words, all we have to do is to get the gradient of this line. Once we get the gradient of this line, it will be equal to the acceleration of this object, of the runner, at 11 seconds as well. So how do we get the gradient at that point, or the acceleration? In this case, the initial is here, and it is 8 meters per second. The final is at 12 seconds. In that final, if you look at it, it is 4 meters per second. The change occurs in a time interval from 10 to 12, meaning it happens in 2 seconds. So with that in mind, let's see how it comes out. The initial u is equal to 8 meters per second. Final is 4 meters per second. The change in time, final time 12, initial time 10, so the change in time is 2 seconds. So with this, we calculate the acceleration at t is equals to 11 seconds. It comes out as the final minus the initial over the time. The time, it's 2 seconds, so I might as well just drop it here. And then when we work it out, we have -4 over 2, and this gives us -2 meters per second squared. The acceleration will have units of meters per second squared. So notice that when I'm making the substitutions here, I always drop out the units. But first I check, before I even make the substitutions, I check to make sure that my units are the same. This is velocity and this is velocity. If I'm going to subtract them, I have to make sure that they have the same units. That's the only way they can subtract. If they have different units, then I'll first have to convert from one unit to the other so that they have the same units. And then lastly, these values of velocity have a unit of time there, the second. And then this one also has the second. So even the value of time I'm going to use, I have to make sure that it has the same unit. I'm just putting it out there so that if we come up with across a question that requires the conversion, we know exactly what we're doing. Okay, so this was the question that we started with. With that, we have answered everything to do with this question. Let's quickly look at another question just to help you guys practice. So I got this question from one exam paper. It carried 11 marks altogether. So I hope you guys will be able to follow through on how we work it out. In general, it is a simple question. Let's see how we approach it. Well, what is the question saying? A car starts from rest and accelerates uniformly, reaching a velocity of 25 meters per second after traveling 100 meters. It travels at this velocity for 750 meters, then it decelerates uniformly and comes to rest in 5 seconds. Use the method of velocity time graph to find its displacement in the first 20 seconds, find its total displacement, and the total time taken. Okay, so how do we work out this question? Well, easy. Let's go through it one more time. So they want us to use the method of velocity time graph. So we're going to just make a simple sketch of what is happening here. So a velocity time graph, we have our vertical axis, we have our velocity here in meters per second. The horizontal, we have our time. And this is in seconds. What is happening? Well, it starts by saying a car starts from rest, accelerates uniformly, reaching a velocity of 25 meters per second. So from rest, we started from here, from the origin, uniformly. So we have something like this until when the velocity becomes what? 25 meters per second. So this has to be 25 meters per second. Just write a 25 since I already have the units up here. Okay, what happens next? It reaches the 25 meters per second after traveling 100 meters. So I'm just going to keep it down here. Maybe I should even use a different color because I don't want this to confuse me very much. So it covers 100 meters as it reaches that 25 meters per second. It covers 100 meters. What else are they saying? Well, if we continue, they're saying it travels at this velocity. What velocity? That 25 meters per second it acquired. It travels at this velocity for 750 meters. So it's like this car maintains this velocity and it maintains it as it covers a distance of 750 meters. 750 meters. Okay, what else are they saying? Well, so it maintained it and covered that distance, the 750 meters. Then it decelerates uniformly and comes to rest in 5 seconds. So it then decelerates uniformly and comes to rest in 5 seconds. So we have something like this. We don't really know what the time is. All we know is it decelerates and comes to rest in 5 seconds. I'm just going to write this down here. I don't really know how it's going to work so far. So this is what the question has given me. I've created a diagram just to help me understand what is happening. Well, how do we proceed from here? The question is asking us a number of things. First, they're saying find its displacement in the first 20 seconds. So this gives us a question. This 20 seconds, when do we achieve 20 seconds? See, if 20 seconds is achieved before the velocity becomes constant, before reaching the 25, let's say we achieved 20 seconds, let me use blue here. Let's say we achieved 20 seconds here. It would mean that we are within the right angled triangle, meaning when they're saying find its displacement in the first 20 seconds, we use the area of a triangle because the time will be 20 here, the height will be whatever that is, the distance will be 100. My point being here, if we have to find out, how far this object goes. Sorry, not that. We want to find out what the time will be as it reaches 25 meters. If the time will be less than 20, then we know it will probably reach 20 seconds after that point. We want to have a clear picture on what shape we have to use to get the distance. Because the question is saying, how far does it go in the first 20 seconds? So I just want to check the 20 seconds. When do we reach it? Do we reach it here? Or maybe we surpass this mark, it is in this region, or maybe it is this side. Maybe the 20 seconds occurs towards the third section of the motion. That's what I'm trying to do here. So how do I do that? Well, I will start by getting the time for the first part. So I'll ask myself, well, how long does it actually accelerate to reach that 25 meters per second? How long does it take to accelerate up to that point? Because once I know the time here, I'll know whether the 20 seconds is to the left of this time or after that time. So how would I do that? Well, I know that this shape is a triangle, so I can get its area, or its area will be given by A is equal to half AB or BH, depending on what you want to use. But I'll get this as my A, I get this as my B, so that, but we know what the area is. The area is equivalent to the distance moved. And we know in the first part, as it reaches that 25 meters per second, the distance it covers is 100 meters, meaning the area will also be 100, since the distance moved is equivalent to the area under the graph. Since I'm given the distance, that distance will be the area. So this is half. A is the time it takes to reach that 25 meters per second. So I'll just write it as T1. I'll keep this as T1. So at this point I have T1. Okay. B is the height. The height is that velocity it reaches, 25. So you see from here that I can literally work this out for what T1 is. So if I cross multiply here, I have 200 is equal to T1 times 25. And here you can divide through so that you have T1 is equal to 200 over 25, and this becomes equal to 8 seconds. So what this is telling us is that actually the acceleration in the first part lasted for 8 seconds. So it took this car, or this was for a car, yes. It took this car 8 seconds to reach that 25 meters per second. Remember our goal is to establish where the 20 seconds is. Is it in the first part before, as in while accelerating, or is it after? So by finding this as 8 seconds, we know to say definitely the 20 seconds elapsed after this part. Probably maybe somewhere here or somewhere there. So again, I want to be sure. Does it take place, or do we reach the 20 seconds in this gap? Or maybe we reach it in that margin. So how do I do that? How do I establish that? It kind of requires me to have an idea of what the second value of time is. How long does it take the car to reach that point? If I know the value of time here, then I'll know whether the 20 seconds will elapse here or in the last section. So how do I do that? Well, to find how long it takes to actually move this region, we utilize the fact that, again, the area here has to be in magnitude equivalent to that distance the object moves. Here we're dealing with a rectangle. So since we're dealing with this shape, we can easily get or write its expression for the area. So the area for that shape will be equal to, I can say LB, so I can say this is L, our B is still this one here. So I have LB. So in this case, our L is the time from T1 to T2. So T1 to T2. Okay, so that will be our L. So I can say L is T1, not T1. We can try to say this is T2 minus T1. Notice what T2 minus T1 is. It's like I'm saying Okay, let me just use a different color here. So it's like I'm saying here, the time, let's say here the time is 8. So if I know the time here, I'm just saying this is t. The difference between t and 8 will give me the time that will last between these 2 points. The time it will take to cover that 750. That is why I'm saying t2 minus t1, so that I get the time it takes to cover that, or I get the length L, or the value of L there. That's why I'm doing this. But we already know what T1 is. So now we have T2 minus 8. This is what gives us that L. But we know what our B is. Our B is the height, which is 25 meters. No, not 25 meters, 25. Let's just take it as 25. So this is 25 this side, so this is times 25. And lastly, we know what the area under the graph there is. It's 750. So I have 750 here and 750 down here. Notice that we're just working it out for that second value of time, T2. So if we do that, this expression now becomes, we just have to simplify this a little bit further. Okay, so if we simplify this, how will it become? So, well, we just have to multiply the 25 inside, so we have 750 is equal to 25 T2 minus, then we have to multiply that 28 by that 8 by 25. So we have 8 by 25. We get 200. So here we have minus 200. Then we simplify this. We now have 25 T2 is equal to 750 plus 200 when the 200 crosses. So now we have T2 equal to 750 plus 200 over 25. So if we do that, we have 200 plus 750 divided by 25. We get 38. So this comes out as T2 is equal to 38 seconds. Now notice what we have. It's like we have our velocity time graph now, how it looks like. In the first part, the car accelerates, and it accelerates for 8 seconds. And it maintains this velocity such that the time now here is 38. Notice the way I worked it out. T2 here was not giving me from here to there, but T2 I got it to give me from the origin all the way up to there. Since to get it, I used T2 minus T1 so that I only get this part. So T2, when I find it, it's the value of time measured from the 0 point all the way up to there. And lastly, the last part was, I was told to say that it takes 5 seconds to reach that point. So when I add the 5 seconds to the 28, to the 38, obviously this is going to be 43. So it's basically just 38 plus 5, which gives me 43 seconds. So this is time in seconds. This is velocity in meters per second. So basically this is the velocity time graph that I'm dealing with here. So what was I looking for? What was the goal? Well, I wanted to know where the 20 seconds was. And by knowing the time here and the time here, I know definitely my 20 seconds, I can approximate it and say that, yeah, maybe my 20 seconds is here. So let's say my 20 seconds occurs there. The question was asking me to find the distance it covers in the first 20 seconds. I know in the first part here, it takes 100 meters. So all I need to know is here, how long does it take? How long, no, not how long, how far does it move here? In the first part, it moves 100 meters. How much further does it move in that part? So in this part, notice that the horizontal length or the gap there, since this is 8, that is 20. So the distance there has to be a 12. So the change that occurs there has to be a 12. So the shape we're dealing with here is a rectangle. So I can say this is my rectangle here. I want to get the distance here. So I'm basically just going to use the area under the graph. The base is 12. The height here is still that 25. So I can easily get the distance under the graph, or the area under the graph, which will be equal to the distance moved. So for this shape, if we tried it, what we're saying is the area for that rectangle we've just created will be L times B, but we have the length is 12, then the height is 25. So that is what we have for that particular shape. So if we worked it out all the way, so we have 12 by 25, and we're getting a 300 there. So here we're getting a 300. So we have a 300. And after that, lastly, we now have to combine this. See, the 300 we have obtained, it's basically for the rectangle that we created. And this rectangle was from 8 to 20. But the shape they want is for the first 20 seconds, meaning that it has to include the 100 meters here. We found 300 here, so it's the 100 meters here plus the 300. Remember, when we're getting the 300, we're calculating it as the area under the graph. But we know this is what actually gives us the distance moved. So you can add this plus the first 100, so that the distance moved in the first 20 seconds is actually equal to 400 meters. So this becomes the distance moved in the first 20 seconds. Okay, so with that, we can now move on to look at the next part, find its total displacement. So to get the total displacement, notice one thing. We have actually already obtained, since not really obtained, look at this. We already have the 100 meters as it was accelerating to 25. And the question gave us the distance it moved as it maintained the velocity. This was given as 750. All we need is to get the distance it moves as it decelerates. So this is all we need here, the distance it moves as it decelerates. And again, the question told us to say that this was 5 seconds. It decelerated for 5 seconds. And we know to say this height here is a 25. And this is a triangle. So you can easily get the area of a triangle again as half by the 5 by the 25. So if we do this, this is going to give us the area of this small triangle at the end as 62.5 as the area. But we know the area under the graph is equal to the distance covered. So now we know the distance covered in the first 8 seconds. And again, the distance it covers in the second part as it maintains the velocity. And we have just found the distance it covers as it comes to rest in that final 5 seconds. So if we added these 3 distances, what we're getting is the total distance covered by this object or by this car. So how do we get that? Well, total distance is now equal to the first 100 plus the 750 plus the 62.5. And if we add this, we're getting the total distance as 912.5 meters. This is the total distance it covers during this interval, or during its total journey. What else is happening here? Lastly, the total time taken. Well, we already found the total time taken. Let's go back to our graph. We already found that up to this point, it covers, let me use something that looks more clear. Okay, so we already found that as it covers from here all there, or as it moves from there, let me use something more visible, dark blue. As it moves from point 0 all the way up to this part, the time we found here was T2, and this was 38 seconds. But it takes an extra 5 seconds to come to rest. So just add the 5 seconds to the 38, and we saw how we got this as a 43. So the total time of this journey is going to be a 43 seconds. So total time is basically just 43 seconds. We already showed how we got this value. Okay, so this was something very easy, took a bit of time, but I hope you guys were able to follow. So for our next video, we're now going to start looking at some more equations. We're going to focus on equations of linear motion instead of the velocity time graphs. If you guys want me to make more videos on velocity time graphs from past exams, you can just comment, let me know in the comment section. But otherwise, in the next video, we're going to start looking at equations of linear motion and how to use them. All right, so we'll see you guys in the next tutorial. This was your tutor.